Hello everyone, it's my pleasure to present our study, Computing Graph Edited Distance via Neural Graph Matching in the VLDB conference. In this paper, we study the problem of graph edited distance computation. Like edited distance on string, the graph edited distance is a perfect choice to measure graph similarity and is widely used in graph search queries. However, given the difficulty of GED computation, existing studies on exact algorithms, such as A-star search, mostly suffer from the severe problem of scalability. They are usually intractable when the graph size is larger than 16 nodes. Therefore, we focus on finding an inexact solution. Given a graph pair, G1 and G2, we aim to find an edit path that transforms G1 to G2 as short as possible. This figure gives a simple example of graph edit distance and edit path. To convert G1 to G2, we could sequentially do the following three edit operations. Add a equal node 3, and add an edge between 1 and 3, and finally add an edge between the node 2 and node 3. These edit operations finally form an edit path, converting G1 to G2. Since the final target is to make G1 isomorphic to G2, there is a node matching relation between G1 and G2 behind the edit path. In practice, all exact search algorithms explore the solution space by enumerating node matchings instead of edit operations. In general, existing methods can be divided into three categories. Compared to the standard A-star search algorithm, A-star beam search uses an extra parameter beam size to control the maximum number of nodes in the queue. Greedy algorithms replace the edit distance metric by a similar greedy function, which can be easily optimized by finding a minimum weight matching in cubic time. As for machine learning models, they first use a graph neural network to generate embeddings of the given graph pair, then combine them to capture the graph-to-graph information. After model training, these GNN-based models can predict the GD value of a graph pair in linear time with extremely low errors. This approach treats GD computation as a regression problem, and a major limitation is that it cannot generate an edit path, which substantially reduces the interpretability and usability of the solution. In addition, the predicted GD value can even be less than the true GD value. In this case, the solution is called an invisible solution, and a feasible edit path for such predicted GD value may not exist at all. For example, if the graph edit distance between G1 and G2 is 3, in this case, the existing models may predict that we need about 2.7 edit operations to convert G1 to G2. To find a high-quality edit path together with the predicted GD value, we propose a novel deep learning framework that solves the GD problem in a two-step manner. First, a GNN-based model is used to simultaneously predict the GD value and a node matching matrix. Second, a post-processing algorithm based on the k-best matching algorithm is used to derive k possible node matchings from the matching matrix generated by our model. The best one will finally result in a high-quality edit path. This figure is an overview of our proposed model GD-GNN. For a given graph pair G1 and G2, the model first generates their node embeddings H1 and H2 using a graph neural network. Then we use two separate cross-matrix modules to capture the node-to-node correspondence between H1 and H2. The cross-matrix modules use trainable parameter matrices which connect H1 and H2 to predict the graph matching and the matching cost. Finally, GD-GNN predicts the similarity score of G1 and G2 by calculating the weighted sum of costs in a cost with a Bayes value. The cross-matrix module takes the node embeddings of G1 and G2 as input, and finally outputs a matrix of square size. This is obviously time-consuming in both model training and testing. but necessary to further generate node matching and edit paths. The inner structure of this module is clear and concise. Suppose that the node embedding size is D. In another word, the size of H1 is N1 times D, and the size of H2 is N2 times D. Using a parameter matrix of size D square, we can directly connect H1 and the transpose of H2 by matrix multiplication. In practice, we simultaneously use C parameter matrices, and hence the size of output becomes N1 times N2 times C. Then we use an MLP to remove the extra dimension, reducing its size from C to 1. The matching matrix A match is a prediction of the ground truth matching matrix, and reflects the extent of matching of different node pairs. Its generation is supervised by the ground truth matching matrix. During the training process, a binary cross-entropy loss is used to minimize the difference between the predicted matching matrix A match and the ground truth one. The cost matrix A cost is generated by another cost matrix module. In this matrix, an element A cost UV denotes the cost of edit operations caused by the node pair U and V. Combining the matching and cost matrices, we can predict the GD value using such a formula. In the following, I will introduce the second step of our framework, how to extract node matching from the predicted matching matrix A match. This task can be formulated as a weighted bipartite matching problem. Specifically, we can construct a bipartite graph G using the predicted matching matrix A match as the edge weights, and then find the maximum weight matching on G. To further increase the chance of finding a short edit path, we explore k-best matchings instead of only the maximum weight one. This figure gives a running example of the post-processing algorithm. In the matching matrix, each element is a real value between 0 and 1. Here, for ease of presentation, it is enlarged to an integer between 0 and 1000. We can see that, in this example, the maximum weight matching M1 results in 5 edit operations. But the second best one, M2, leads to the best solution, only 2 edit operations. The below part of this figure shows how we convert the second best matching M2 into edit operations. In the following, I will give a brief introduction to the k-best matching algorithm. A key concept in this algorithm is solution space splitting. Given a graph pair G1 and G2, the whole solution space denotes the set of all node matchings between them. We can easily split the whole solution space into 2 subspaces by branching on a node pair as follows. The subspace S1 denotes the set of node matchings which contain the given node pair, and S2 denotes the set of matchings not using it. To find k-best matchings, we aim to maintain a sequence of solution subspaces S1, S2 to Sk, which satisfies that the best matching of Si is exactly the ith best matching of the whole solution space. Then we focus on the second best matching of each subspace. The best one among all second best matchings is the k plus 1th best matching of the whole solution space. This is a demo of the k-best matching algorithm. There are 4 subspaces from S1 to S4, and we have already calculated the top 2 matchings of each subspace. Suppose the second best matching of subspace S3 has the largest weight among all second best ones. Then we can split S3 into S3 and S5. The original best matching remains as the best matching of S3, but the original second best matching becomes the best one of the new subspace S5, and also denotes the 5th best matching of the whole solution space. After splitting, we need to recalculate the second best matchings of S3 and S5. In this way, the problem of finding k-best matchings is solved by iteratively finding second best matchings. Many well-known graph algorithms support that we can find the best or second best matching in cubic time. Hence, the total time complexity of finding k-best matchings is O k times the cubic of n. Although the cubic time complexity is not efficient enough for large graph processing, it is still time-saving compared to search-based algorithms. In the following, I will give a brief introduction to the experiments. We test our method on 3 real graph datasets and synthetic parallel graphs. The statistics of these graph datasets are listed in this table. Each real graph dataset consists of hundreds of graphs within 100 nodes. Note that the calculation of graph added distance is based on graph pair, so the training and testing datasets is actually much larger. In addition, we generate some synthetic parallel graphs in large scale for performance evaluation. We vary the number of nodes in the parallel graphs from 25 to 400. Since all graphs in ACE and Linux have no more than 10 nodes, we simply use exhaustive search to generate the ground truth data on these small graphs. But due to the NP hardness of GD computation, the ground truth data of large graphs is generated in a suboptimal manner instead. Specifically, given a source graph G1 and the expected GD value T, we randomly conduct T-edit operations on G1 to get the target graph G2. In this way, a synthetic graph pair is generated efficiently. In performance evaluation, we divide our competitors into 2 groups. The first group, SIMGNN, TAG-SIM, and GraphPath Network, are pure machine learning models which can only predict GD values. The second group calculates graph edit distance by finding an actual edit path. Since our framework can both predict GD value and extract a node matching, we use GDGN value and GDGN matching to compete in each group, respectively. Our proposed algorithm, GDGN matching, greatly outperforms the other 2 node matching methods in all datasets. In principle, the feasible rates of all node matching algorithms should be exactly 100%, since they output an upper bound of the graph edit distance. However, we can see that the feasible rate of GDGN matching on MDB large is 99.9%. Recall that the ground truth GD value of a large dataset is obtained by generating synthetic graph pairs. Such pseudo-ground truth may be larger than the true GD value with a very low probability. For such cases, GDGN matching can find a better solution than the pseudo-ground truth. In this experiment, we evaluate the effectiveness of our k-best matching framework given the matching matrix image produced by GDGN when we vary the size of k from 1 to 100. Besides our method GDGN matching, 2 matching matrix generators are used as a baseline for comparison. The red line GDGN untrained generates the matching matrix using an untrained GDGN model. In this case, random initial parameters result in a random matching matrix. The blue line, greedy, generates the matching matrix using a heuristic greedy function. The results show that the mechanism of finding k-best matchings actually works for all meaningful weight matrices. Our model GDGN does learn something from the graph dataset and predict a matching matrix which is much better than greedy heuristics. In this paper, we propose a novel deep learning framework that solves the GD problem in a 2-step manner. First, the graph neural network is in charge of predicting the GD value and the matching matrix. Second, a post-processing algorithm based on k-best matching is used to extract multiple node matchings from the matching matrix generated by our model. The best of them will finally lead to a high-quality edit path. The post-processing algorithm is a key innovation that makes up the gap between what graph neural networks can produce and an actual solution to the GD problem. Thank you very much for watching this video.